Welcome to the first video lecture for Chapter 8. This is hypothesis testing, and for 8.1 we're going to just talk about the basics of hypothesis testing. This is for STA 2023. So in this section we're going to present key components of a formal hypothesis test. The concepts in the section are general and apply to a hypothesis test that involve proportion, means, standard deviations, or variances. So hypothesis. In statistics, a hypothesis is a claim or statement about a property of a population. The hypothesis test, or the test of significance, is a procedure for testing a claim about a property of a population. So, for example, majority of consumers are not comfortable with drone deliveries. 1,009 consumers were asked if they were comfortable with having drones deliver their purchases, and 54% of them responded with no. Using P to denote the proportion of customers not comfortable with drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half, or P is greater than 0.5. Now, the expression P is greater than 0.5 is the symbolic form of the original claim. The big picture. We have the claim that a population proportion P is such that P is greater than 0.5. Now, among the 1,009 consumers, how many do we need to get a significantly high number who are not comfortable with drone delivery? So a result of 506, or 50.1%, is just barely more than half. So 506 is clearly not significantly high. Now a result of 1,006, or 99.7, is clearly significantly high. But what about the result of 545, or 54%? That was obtained by the Pitney Bowes survey. So is 54% significantly high? The method of hypothesis testing allows us to answer the key question. Using technology. It's easy to obtain hypothesis testing results using technology. In this course, I'm going to show you how to use Excel to obtain that. Now, the accompanying screen display shows results from 4 different technologies. So we can use computers or calculators to do all of the computational heavy lifting. So here we have StatDisk, Minitab, the TI-8384, and StatCrunch. And all of those results, we're going to learn how to interpret them when we do hypothesis testing. So, examining the 4 screens, we see there's some common elements. They all display a test statistic. They all include a p-value. So we're going to focus on understanding how hypothesis testing procedure works and then learn the associated terminology. Often, then, will the technology make sense, or the results from the technology. So significance. Hypothesis tests are also called tests of significance. Now in section 4-1, we use probabilities to determine when the sample results were significantly low or high. In this chapter, we formalize those concepts in a unified procedure that is used often throughout many fields of application. Null hypothesis. The null hypothesis, denoted by H null or H0, is a statement that the value of the population parameter, such as proportion, mean, or standard deviation, is equal to some claimed value. The alternative hypothesis, denoted by H1, HA, or H capital A, is a statement that the parameter has a value that somehow differs from the null hypothesis. For the method of this chapter, the symbolic form of the alternative hypothesis must use one of these symbols: less than, greater than, or not equal to. Now, here's the 5-step procedure. Now, I know they have it here as 7 steps, but I'm going to show you how to do this. Actually, they have it in 8 steps. We're going to show you how to do this in 5 steps. First thing is we identify the claim, give the symbolic form, identify the null and alternative hypothesis, select the significance level, identify the test statistic. We either use the p-value method or the critical value method, right? You find the values, you make a decision, either one that you use, and then we restate the decision in non-technical terms. Confidence interval method. So we can use the confidence interval method with a confidence level selected in order to do hypothesis testing. Now, because the confidence interval estimate of a population parameter contains likely values of that parameter, we reject the claim that the population parameter has value that is not included in the confidence interval. Again, significant level for hypothesis test, that's your alpha, a 2-tailed test, and a 1-tailed test. So one of the things that I do want to tell you that since we are going to use either less than, greater than, or not equal to, each one of these symbols for the alternative hypothesis refers to a specific test. Less than will be a left-tailed test, greater than will be a right-tailed test, and not equal to will be a 2-tailed test. So, for step 1, identify the claim to be tested. Step 2, give symbolic form. 3, consider the 2 symbolic expressions obtained so far. Alternative hypothesis H1 is the one not containing equality, so H1 uses the symbol of less than, greater than, or equal to. The null hypothesis is the symbolic expression of the parameter equals a fixed value being considered. So the null hypothesis is always equal to. So given the claim that the majority of consumers are uncomfortable with drone delivery, we can apply steps 1, 2, and 3 as follows. We identify the claim to be tested and express it in symbolic form. Using P to denote the probability of selecting a consumer uncomfortable with drone delivery, the claim that the majority is uncomfortable with drone delivery can be expressed in a symbolic form as P is greater than 0.5. Give the symbolic form that must be true when the original claim is false. If the original claim of P is greater than 0.5 is false, then P is less than or equal to 0.5 must be true. So this step is in 2 parts. We're going to identify the alternative hypothesis and identify a null hypothesis. The null hypothesis is pretty straightforward. It's always symbolic in expression and the parameter equals some fixed value being considered. So we're always going to get that null hypothesis as P is equal to some value K. The alternative hypothesis, we're going to use symbolic expressions. P is greater than 0.5 and P is less than or equal to 0.5. So the alternative hypothesis, H1, is the one that does not contain equality. Of those 2 expressions, P is greater than 0.5 does not contain equality. So we get that H1 is P is greater than 5. So this is what they consider to be a right tail test. Significance level. The significance level alpha for the hypothesis test is the probability value used as a cutoff for determining when the sample evidence constitutes a significant evidence against a null hypothesis. By the nature of the significance level alpha is the probability of us mistakenly rejecting the null hypothesis when it's true. So again, significance level alpha is equal to the probability of rejecting the null hypothesis when the null hypothesis is true. Significance level alpha is the same alpha introduced in section 7.1 where we define as critical values. Common choices for alpha is 0.05, 0.01, and 0.1, where 0.05 is the most common. Step 5, we'll identify the test statistic that is relevant to the test and determining sampling distribution. The table in the following slide lists the parameters along with corresponding sampling distributions. So if we're doing a proportion, the sampling distribution is the normal Z, and the test statistic is the formula here all the way to the right. Now, if we're using a T, which is mean mu, we use this formula. If we're using the normal Z, in other words, sigma is not known in normally distributed population, or sigma is not known and n is greater than 30, we can go ahead and use the Z. Or we use the T when sigma is not known in normally distributed population, or sigma not known and n is greater than 30. We don't use the chi-square, the bottom one, for this course. Now, the claim that P is greater than 0.5 is a claim about the population proportion P. So we use a normal distribution provided that the requirements are satisfied. When n is equal to 1009, P is 0.5 and Q is 0.5. On the ongoing example, n times P is greater than or equal to 5, n times Q is greater than or equal to 5 are both true. Step 6, find a value of the test statistic and the p-value or the critical value of values. If it's a two-tail test, you have a plus or minus critical value. If it's a left tail or right tail, you'll have either a negative for a left tail critical value or positive for a right tail critical value. Test statistic. The test statistic is a value used in making a decision about the null hypothesis. It is found by converting the sample statistic, p hat x bar s, to a score such as z, t, or chi-square, with the assumption that the null hypothesis is true. The default setting is that the null hypothesis is true. So we have a claim about the population proportion P. We have that n is 1009, x is 545, so p hat is 0.54. With the null hypothesis of P is equal to 0.5, we're working with the assumption that P is equal to 0.5. And it follows that Q is equal to 1 minus P, which is also 0.5. Now we can evaluate the test statistic as shown below. The test statistic of Z is equal to 2.55 from each of the previous technology displays is more accurate than the one below. If we replace 0.54 with the ratio 545 over 1009, we have 0.54013,875, so we get a Z is 2.55. Now, if you notice the formula that you use, they got the test statistic 2.54. Critical region. Critical region or rejection region is the area corresponding to all values of the test statistic that cause us to reject the null hypothesis. Two-tail test. The critical region is in the two extreme regions under the curve. So the gray area here is what they call the rejection region. The orange colored over here is the non-rejection region. Left tail test, the critical region is the extreme left. So any value that's in this tail will cause us to, that's the rejection region, or to reject the null hypothesis. And then the right tail test, any value over here in this gray region will cause us to reject the null hypothesis. So remember, anything, if it's a two-tailed test, in this region, we do not reject. Anything to the right for a left-tailed test in this critical value, we do not reject. And then for a right-tailed test, anything to the left. P-value method. In a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming that the null hypothesis is true. Now, using the data from the previous problem, the test statistic is z is equal to 2.55, as a normal distribution area of 0.0054 to its right. So a right-tailed test with a test statistic of z 2.55 has a p-value of 0.0054. So again, we can see the different technology displays given earlier and know that each of them provides the same p-value of 0.005 after rounding. So here we go. We're going to start with the testing, left tail, right tail test, right? And so if it's a left tail test, p-value, area to the left of the test statistic. Now, is the test statistic to the right or to the left of the center? P-value is equal to twice the area to the left of the test statistic. If it's a right tail test, twice the area to the right of the test statistic. And then, of course, right tail test, area is equal to the right of the test statistic. Again, doesn't matter which one of these we look at. If it's a left tail test, anything in the gray area, we reject. And if it's a right tail test, anything in the gray area, we reject. So, some caution, don't confuse the p-value with the parameter p or the statistic p hat. Critical value method. In the hypothesis test, the critical value of values separate the critical region where we reject the null hypothesis from the value of the test statistic that do not lead to rejection of the null hypothesis. So the critical value is shaded in green here, actually sort of grayish. So the figure shows that with significant level alpha of 0.05, the critical value is z is equal to 1.645. So again, anything in this grayish area, we reject the null hypothesis. And we saw that we got a z value of 2.55, or a test statistic of 2.55, which is clearly in the rejection region. So the next step is make a decision to either reject the null hypothesis or fail to reject the null hypothesis. So the decision criteria for the p-value method. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. So we're going to restate the decision using a simple non-technical term. Let me go back here. This is the same thing with the critical value. If the test statistic is in the gray area, so if it's a right tail test, if it's greater than the critical value, then we reject the null hypothesis. If the test statistic is actually in the non-rejection region, or it's less than, we do not reject the null hypothesis. So there is sufficient evidence in this case to support the claim that the majority of consumers are uncomfortable with drone deliveries. Now, wording the final conclusion. For help in wording the final conclusion, refer to the table next slide, which lists 4 possible circumstances and the corresponding conclusions. Note that only the first case leads to wording indicating support for the original conclusion. If you want to support some claim, state it in such a way that it becomes the alternative hypothesis and then hope that the null hypothesis gets rejected. So, original claim does not include equality and you reject the null hypothesis. There is sufficient evidence to support the claim. Now, condition, original claim does not include equality and you fail to reject the null hypothesis. There is not sufficient evidence to support the claim. Condition, original claim includes equality and you reject the null hypothesis. There is sufficient evidence to warrant rejection of the claim. And then the last one, original claim includes equality and you fail to reject the null hypothesis. There is not sufficient evidence to warrant rejection of the claim. So we always write it in terms of the alternative hypothesis. So accept or fail to reject. We should know that we fail to reject the null hypothesis instead of saying that we accept the null hypothesis. The term accept is misleading because it implies incorrectly that null hypothesis has been proved, but we can never prove a null hypothesis. The phrase fail to reject says more correctly that the available evidence isn't strong enough to warrant rejection of the null hypothesis. Sometimes they use multiple negatives. Final conclusions can include as many as 3 negative terms. For such confusing conclusions, it is better to restate them to be understandable. Instead of saying that there is not sufficient evidence to warrant rejection of the claim or no difference between 0.5 and the population proportion, a better way would be until stronger evidence obtained, continue to assume that the population proportion is equal to 0.5. Next thing is a confidence interval estimate of the population parameter contains the likely values of that parameter. We've talked about this in class. We should therefore reject the claim that the population parameter has a value that is not included in the confidence interval. Now we have to be careful when we're using the confidence interval method for hypothesis testing. If it's a proportion, is the confidence interval equivalent to a hypothesis test in the sense that they always lead to the same conclusion? For a proportion, the answer is no. For the mean or standard deviation of variance, the answer is yes. We're going to talk briefly about type 1 and type 2 errors. Type 1 errors, the mistake of rejecting a null hypothesis when it's actually true. The symbol alpha is used to represent the probability of a type 1 error. So alpha is equal to the probability of type 1 error, which is equal to the probability of rejecting a null hypothesis when the null hypothesis is true. Type 2 error, the mistake of failing to reject a null hypothesis when it's actually false. The symbol beta is used to represent the probability of a type 2 error. So beta is equal to the probability of the type 2 error, which is equal to the probability of failing to reject a null hypothesis when the null hypothesis is false. In other words, we do not reject a null hypothesis, but it turns out that the null hypothesis is actually false. In other words, the alternative hypothesis should have been the one. So we should have rejected the null hypothesis and we didn't. So here's a table that kind of makes it a little easier. So reject a null hypothesis, type 1. Reject a true null hypothesis is a type 1 error. Fail to reject a null hypothesis is a type 2 error, and that's known as beta. So consider the claim that a medical procedure designed, here's another example describing type 1 and type 2. Consider the claim that a medical procedure designed to increase the likelihood of a baby girl is effective. So the probability of a baby girl is P is greater than 0.5. Given the following null and alternative hypothesis, we're going to write a statement describing the type 1 error and type 2 error. Null hypothesis, P is equal to 0.5. Alternative hypothesis, P is greater than 0.5, which is the original claim that will be addressed in the final conclusion. So type 1 error. Type 1 error is the mistake of rejecting the true null hypothesis. So the following is a type 1 error. In reality, P is equal to 0.5, but the sample evidence leads us to conclude that P is greater than 0.5. In this case, a type 1 error is to conclude that the medical procedure is effective when in reality it has no effect. Type 2 error is the mistake of failing to reject the null hypothesis when it's false. So the following is a type 2 error. In reality, P is greater than 0.5, but we fail to support the conclusion. In this case, a type 2 error is to conclude that the medical procedure has no effect when it really is effective in increasing the likelihood of a baby girl. And that's the end of point 8.1. Thank you.